This is FE Peer Review. The date is May the 5th, 2021. This is a review of a scientific research paper regarding atmospheric refraction prepared by the U.S. military. From time to time, a flat earther treats us to a long-distance observation, usually over water, often over the ocean, claims, quote, "we see too far," and proceeds as if there is no such phenomenon as atmospheric refraction. Many science areas, industries, and other organizations concern themselves with atmospheric refraction. Science areas like astronomy, applications like radar, industries like telecommunications, and as far as other organizations, perhaps the most significant is the U.S. military. Where visual means are used for targeting, accounting for atmospheric refraction can play a critical role in the success or failure of hitting a target. Given the consequences of missing a target, the world's militaries take the issue seriously and invest serious resources into understanding atmospheric refraction. Today I'd like to share a paper with you all, which was prepared by the Institute for Defense Analyses, IDA, for the Defense Advanced Research Projects Agency. This is the IDA About Us page. It says here, Institute for Defense Analyses is a private nonprofit corporation headquartered in Alexandria, Virginia, just outside Washington, D.C. IDA's mission is to answer the most challenging U.S. security and science policy questions with objective analysis, leveraging extraordinary scientific, technical, and analytical expertise. Alexandria, Virginia is home to a lot of defense-related companies. And here's a page on DARPA, Defense Advanced Research Projects Agency. DARPA is an agency within the Department of Defense, so it's a federal agency, listed down at the bottom here. And it's essentially a research arm for the U.S. military. In the future, if you should find yourself in a discussion with a flat earther and the issue of atmospheric refraction comes up, hopefully this video will be a useful reference. The primary purpose is not to explain the science behind it, but simply to point out that this is an issue of concern to military organizations, and as such, there must be some substance to it. They are not about to waste money on something which does not contribute directly to their defense purposes. The paper I'm looking at here is available online, and there's a link in the description. I will also include links to some other papers. However, the copy we're looking at on the screen is my own downloaded copy. I did this so that I could highlight the parts I thought most relevant. I'm not going to go into all the tables and equations. Feel free to pause the video and read what's on the screen, or download a copy yourself from the links. I will just be pointing out the main items and issues this paper raises, issues which are clearly real-world phenomena important enough to warrant study and expense on the part of the U.S. military. Let's begin. The effects of atmospheric refraction on long-range near-surface electro-optical sensing over water, prepared for DARPA, prepared by the Institute for Defense Analyses. The paper was from 1996. An introduction to the problem. There is a problem. Modern electro-optical sensors are much more sensitive than the human eye, so they can detect a target much farther away than a human observer can. However, these sensors look through a long optical path in the atmosphere, in excess of 10 kilometers over water, and properties of the atmosphere that normally do not affect human seeing can be important. The optical phase change associated with refraction correction provided by eyeglasses, say 2 millimeters of glass, is equivalent to a 0.3% change in density of 1 kilometer of air. Eyeglasses are used to see objects about 100 to 200 meters away, while modern electro-optical sensors look for targets up to 10 to 20 kilometers distance. Thus, we now see that the normal variability of the atmosphere can produce significant refractive effects. I'm going to skip over a lot of this. Anybody who wants to can download the paper, read it all in detail. I just want to touch on the main issues. Here's a couple of definitions. Atmospheric boundary layer, ABL, over land. The ABL is roughly the lowest 10% of the atmosphere, the region that shows a strong diurnal variation in temperature profile as a result of solar heating of the ground and subsequent heating of the atmosphere by re-radiation in the infrared. Over land at mid-latitudes, a typical day-night temperature difference is 10 Celsius as compared with 0.3 Celsius over water. Why should we care about this? The refractive effects discussed here can lead to a difference in target visual detection range by a factor of 2 or more, and can also give rise to mirages, which may produce time-varying multiple images of a single target. So why do we care? Because it messes things up if we ignore it, and we miss our target. That's a no-no. The atmospheric boundary layer is typically about 1/2 to 1 kilometer thick. We're particularly interested in the lowest 10% of this layer, so 50 to 100 meters, the atmospheric surface layer, ASL. The surface of the Earth where the temperature, hence the density and refraction, shows its largest diurnal variation, the variation being what's important here. Atmospheric temperature normally changes with height. If warm air overlies cold air, the atmosphere is stable, so warm air over cold air tends to stay that way. Cold air overlying warm air, the atmosphere is unstable, so that's a situation that doesn't last long. It occurs from time to time, but when it does, it tends to be a short duration. The air-sea temperature difference, ASTD, that's a difference between the air above the seawater and the temperature of the seawater. And typically the air temperature is warmer than the seawater, so you're subtracting the lower temperature from the larger. One may ask how ASTD values are obtained. From about the time of World War II into the 1970s, there were a number of weather ships on the oceans, mainly in the North Atlantic and North Pacific, and they measured air temperature at the deck or mast level and sea either by scooping out a bucket of water from the sea and measuring its temperature, or by reading the temperature of the seawater that enters the condenser intake of the ship. I highlighted this section because I wanted to point out that the information, this is not just a bunch of theories that people are making up. This is all derived from physical information and physical evidence. So the temperature differences are not just things people are coming up with off the top of their heads. They're actual measurements taken from the air and from the water by boats on the ocean over the course of decades. The character of the air masses will vary strongly near the continent-ocean boundaries. So we tend to get more pronounced effects where the ocean meets the land because there are more differences in those areas. And that is, of course, our beaches, our frequent long-range observations, such as the recent Blackpool observations or the platform habitat observation. These are typically observations that are occurring in that area where there tends to be the largest effect. When the atmospheric lapse rate is unstable, the high altitude density is large, thus light rays are bent up, and thus the visual range is reduced. So that's the unstable situation. It does occur, and when it occurs, it can actually bend light rays up, but it doesn't last. It's the unstable atmospheric condition. When the atmospheric lapse rate is stable, light rays are bent down. That would be the condition, being stable, that is the most frequent. When atmospheric lapse rate is neutral, light rays in such an atmosphere are slightly curved, being concave down. So at a neutral stage, things still tend to be slightly concave down. I mentioned these three conditions because these describe looming. Looming is the typical condition which happens during when things are stable. The light rays are being bent down towards our eyes, from the distance towards our eyes. And that is the condition that's stable and tend to be mostly occurring. When the refractive effects discussed above are sufficiently large, they may give rise to mirages. Now, the paper has a whole large section on mirages, and it's well worth reading on its own. And I wanted to point out that it's there. But I'm not going to go into mirages here. I just wanted to stick with simple atmospheric refraction, because this video will be long enough as it is, and I wanted to stick to just one point. But I welcome people to download the video and download the paper. The link is in the description. And read the whole thing for yourself if you want. There are some other papers that might be of interest as well. Lastly, the abstract. This is a summary of the entire paper. Modern electro-optical sensors are much more sensitive than the human eye. We read that part at the beginning. Let's see here. This paper begins with a review of variations in the normal atmospheric temperature profile in the lowest 50 to 100 meters above the surface, the atmospheric surface layer, pointing out that the horizontal range for target detection can vary, possibly by more than a factor of 2. Perception of multiple targets produced by a variety of optical mirage phenomena is also discussed. That's the section we skipped over here for now. The purpose of this discussion is to point out the new meteorological concepts and to raise some questions as to the operational significance of refraction that produces multiple images, which the author cannot yet answer. So there you go. The U.S. military is concerned enough about refraction to pay for extensive scientific research in the subject. So if atmospheric refraction simply doesn't exist and is a phenomenon that's been made up by a bunch of people trying to pull the wool over the eyes of the rest of the world, well, explain that to the Pentagon. They'd probably like to know, because they're spending money on this stuff. That is FE Peer Review. Hope you're all having a great evening, and I'm signing out. Good night.